Hey everyone, in this video we're going to be talking about exponential functions. So we're going to talk about what is an exponential function and evaluate them. So beginning with just using a calculator, an exponential function, here's one example. It has a base that's a real number, like this one's 3 for each of A, B, C, D, raised to some power. There's a little bit more to the definition, which we'll go through, but just plugging these values into a calculator, you would type in 3. A lot of calculators have a caret-like button, so you hit this button here, and then you can type in 1.7, and then that's how you would get approximately 6.47. And then same thing with the next one, and that one's about 6.68, and so on. 6.7, and then 3 to the square root of 3, that's going to be 6.7 roughly as well. Alright, so these are exponential functions, and now here is a quick review on some laws of exponents, because these are going to help us out if we're working with exponential functions. So as a reminder, and you may have seen these before, that we have the following rules or laws. So this first one here, this one is called the product rule for exponents. So if you have the same base, notice it's A, so A times A, same base, and you're multiplying, then the rule says that you just add the exponents, okay? And if you ever forget these rules, you could always do a quick example, and that way it'll help you remember the rule. So let's say you don't remember that you're supposed to add the exponents, and you could just do something like this. You say, oh, okay, well, what if I have a simple problem? This is really 2 3 times, and then the second one is 2 twice. And then if you count, that's a total of 5 2s. And then you could tell yourself, oh, well, that's right. I could have just added those exponents. And so that's a way to remember these rules if you ever forget. Okay, so the second one, this is the power rule. So if you have your base raised to a power, and then that quantity raised to another power, another exponent, then that rule says that you multiply. So there's no symbol in between here, but this is S times t. You multiply those exponents. And then the next rule is a product to a power. So notice you have a times b raised to a power, and you can think of distributing here. This is really b to the s, and this is a to the s, so it's just the product with each exponent on the bases. This fourth rule over here is a very nice one. 1 to any power is just 1. And as long as it's not 0, which is over here, we have that as another rule. So 1 is always 1, no matter how many times you multiply it. Number 5 here, this one is the negative exponent rule. I'll show you another version of this, but pretty much if you see a negative exponent, it's really letting you know that your base, A is the base, needs to move. So technically this one is in a numerator. This is like above an invisible fraction bar with an invisible 1 underneath, and so you're moving your base. It's saying, hey, move the base down. So when you move it, then your minus sign comes off and your exponent turns positive. This is the same as saying 1 over a quantity to the s power. Okay, so here's the other version of this rule. Let's say that you started with, let's use another letter. You started with your base in an exponent, your base in the denominator, and your exponent was negative. Okay, then what this also says is that you have to move that base as well, and this time you're going to move it up into the numerator, and then you take off the minus sign. So this rule works in either direction. A negative exponent just means that you move the base. So move the base. If it's in the denominator, move it up. If it's in the numerator, move it down. And then the sixth one, a to the 0 power is just 1. So no matter what this base is, as long as it's not 0, this is 1. So any number, just make up a number here, to the 0 power is just 1. Okay, quick review on exponents. All right, so here is our definition for an exponential function. An exponential function is just a function of the following form, where the base here is a positive real number that's not 1, so we're not interested in 1 to a power, but you have a number here, and then c can be a constant. So c is just some constant in the front, Notice x is what's changing, and it's your exponent. So what I want you to recognize is the difference in exponential functions from previous functions. So previously, pretty much until you learn about exponential functions, your functions look like the base might have been a variable, something like, let's say, x, maybe squared. And now what's new is your base is actually a number. So let's say 2 is your base, and then your exponent is your variable. It's what's changing. So notice that difference. Your base, the bottom number, is a real number. Now the domain is all real numbers. You can plug anything you want into this exponent. And then the base is also called the growth factor. So that's a name for the base. And then we also have what's called an initial value. And that comes from, it's like a starting point. So initially the value of this function is when I plug in 0. It's always this constant c. Okay, so that's just something that we have called an initial value, because a lot of times these exponential functions come up in real life examples, like populations are modeled with exponential functions. So is like bacteria growth or decay, things like that. And so we are usually interested in like a starting point, an initial value, and so that's when we plug in 0. Okay, so for an exponential function, and this is a theorem here, like a mathematical fact, if we have the following that's true, so our base is positive and not 1, and then the leading coefficient, the constant, is not 0, then for any real number, f of x plus 1 divided by f of x equals a. Okay, here's another way to write it. Pretty much what this says is if I take my next term in my values for this function, so notice x plus 1 is like saying the next value for x, and if I divide that by the previous one, which is x, f of x, I get this factor a. Okay, so let me show you an example to make this theorem make sense. So let's say that my function was, let's just pick a nice one, 2 to the x. Okay, so 2 squared is 2 times 2, which is 4. And 2 to the next number, 3, is 8. 2 times 2 times 2. And now if I divide those two numbers, so if I divide the second one by the first one, look what I get. I get the growth factor, 2. And that would happen every time. If I pick the next value for my power, let's say it's 4. Okay, that's 2 to the 4th is 16. And if I divide the next value by the previous one, I get that growth factor. So that's what this theorem is saying. Okay, so let's do this example where we're going to identify if our function is a linear function or an exponential function. So quick reminder, linear functions are lines, straight lines when you graph them, okay? And what's also true about linear functions is that they have a constant rate of change. So when we learned about linear functions, lines, they have a constant rate of change. Another way to call that is a slope, constant slope. So that's for linear functions. Exponential functions, that's not what happens, and we'll be graphing those in the next video so you can see what that looks like. Okay, so determine if the function is exponential, linear, or neither. And if it is linear, we'll find a linear model for it. Okay, and if it's exponential, we'll find an exponential model for it. So we're going to do for parts A, B, and C using the data. And for each function, we're going to compute the slope. So average rate of change is the slope. Okay, so that's slope, which is rise over run, which our formula from the past is the difference in the y's divided by the difference in the x's. So that's what rate of change is asking for. All right, if it's constant, like we mentioned a minute ago, then the function is linear. So constant slope, it means it's a linear function. You will get a line when you graph it. If the rate of change, the slope, is the ratio of consecutive outputs, and that's constant, then it's exponential. Okay, what does that mean? that means exactly what the theorem just said. Okay, so if we divide the second output by the previous one, we should get a number, which is our growth factor. And if we do that again for the third output and the second output and so on, and we get the same number, then it's exponential. Okay, so that was from our theorem, this part here. All right. So from part A, we have our x values and our y values. And between 2 points, so notice this is an ordered pair on our graph. This is the next point on our graph. And if we take the rate of change between those points, or the slope between those points, that's -4. Okay? Then between the next two set of points, the rate of change between those 2 points happens to be -4 also. And then the next 2 points, which is these two, the rate of change is -4, y2 minus y1 over x2 minus x1, and then the same thing for the last two. So we got a constant rate of change of -4 the entire time. And if you want to check for the ratio of the outputs, notice it's not constant. So right away, just from this all being -4, we know this is linear. But if we wanted to check this part for exponential, look what happens. We're getting all kinds of numbers. So that's because what we're doing there is we're taking the next output, we'll call this the second output, divided by the first output, okay, and we're getting a ratio there. And then we do that again for we'll say the next one, so the third output divided by the second output, which is this, we get a ratio there, and so on. And notice it's not constant, so it's definitely not exponential. All right, so the average rate of change was constant. It was -4 for the whole thing. And so therefore the function is linear. Okay, and now that wasn't just the only thing asked. We weren't just asked to find whether it's linear or not. It was also find a function that represents the values that we got from the table. So we know that the slope, or the rate of change, is -4. And then using other points on the graph or from our table, we can find other points to use for our function. Okay, so we can use our y equals mx plus b formula by picking the y-intercept on the graph, which is 0, 2. But you can pick any point on the graph, and just remember you can plug into your point slope form a line. Y minus y1 equals m times x minus x1. So when in doubt, you can always just plug into here. We know m was -4, and then any point on our table of values would go in the place of x1 and y1. And so we get a function that represents that data. It's just a function or equation of a line, but this is a function that represents or models the data from that table. All right, let's do it again for part B. Okay, so here's 2 points from the table. We calculate the slope between them, so y2 minus y1 over x2 minus x1, and we get a number. When we do that again for the next 2 set of points, notice we got a different number, not -54. Right away, we can just stop and say it's not linear. We don't have to keep computing the rate of change, even though we have it here. But at this moment, when these two numbers are not the same, then we said this is not linear. Okay, so then we check if it's exponential. So remember what we just talked about? It's exponential if we take the second output, divide it by the first output, we get a ratio there, and if that ratio is constant for all of our outputs. So if we take our third output, divide it by our second output, and we got the same ratio. And then we do want to check all of them, so we take the fourth output, divide it by the third output, we got the same ratio. Last one, from the given data, the fourth output divided by the previous one, and so on. Or I think that was the fifth output. And so we got 1/3 the whole time. So this is exponential. All right, so the average rate of change isn't constant, so it's not linear. However, the ratio of consecutive outputs was constant, and so it is an exponential function, and that constant ratio is our growth factor, or the base for our function. Okay, so now you have to use an initial value, or any point on the data table pretty much would work here, to find c. But from our data, we already knew that when x was 0, y was 27. So that lets us know that this is c, because of what we talked about. We called c the initial value, and it's what you get when you plug in 0 into the function. Okay, so that's how we knew that this was c. Otherwise, you could solve for this. Like, let's just say you didn't recognize that that was going to be c. If you pick a point from your table, like we had the point 1, 9, you can find out this value of 27 that way. We know that the base was 1/3, so we know right away that our function was some number, some constant, times 1/3 to the x. And using any point from your table, you know that the output is the y value and the input is the x value. And so you can solve for the unknown, in this case solving for c. So we have 9 equals c times 1/3, divide both sides by 1/3, and when you do this you would say 9 times 3/1, you'd flip and multiply, and that's c, and that's how you can solve and get 27. So just showing you another way, an option, in case you didn't realize that c was going to be 27 from this point here, 0, 27. And so that is our model of our exponential function that represents that data set. All right, one more, letter C. So plugging in these points into our slope formula, we get a rate of change, f3. The next 2 points, a different rate of change. So right away, this is not linear because these aren't equal. Okay, so moving ahead and checking if this is exponential, if we say 7 divided by 4, that's that ratio of outputs. And if we do the next 2, we have 11 divided by 7, and that's already not the same ratio, so this is not exponential either. Okay, so this is not going to be linear or exponential function. Okay, so that's going to be it for this first part of the exponential functions. So just remember that for an exponential function, you have a base. We can call it any letter. We've been picking a, but just know it's a number. So your base is a number. It's going to be a positive number other than 1. And then your constant coefficient here, this initial value, you get this when you plug in 0. And then what's changing is your exponent. So your variable is the exponent. So this is going to be where you're plugging in your values in the exponent position. All right, that's it. Thanks for watching.